So thanks everybody offline and online to be coming to my first ever seminar talk, which I call From Hochschild to Gerstenhaber-Schack, as told through drawings of trees and rectangles. The story begins with the work of Hochschild and mainly Gerstenhaber in the 60s on the deformation of associative algebras. Well, this story is beautiful in its simplicity, but yet the question that motivates my talk today is whether we can retell this story, not for a single associative algebra, but for a presheaf of algebras, meaning local algebras with functors between them. This question was posed by Gerstenhaber and Schack in the 80s, and they published some papers on it, resulting in the Gerstenhaber-Schack complex. However, they were soon met with some obstacles, and these were turned into plot twists that my collaborators, Huang Lin Van and Wendy Lowen, my supervisor, and myself were only able to solve recently in two papers. Their paper in 2018 and our paper that's coming out this year. I hope in this talk to be able to transmit some of the intuition that led to our solutions and the framework that we used to come up with these solutions. And I will do this, or I'll try to make this happen through some insightful drawings, hopefully making it a very elementary talk that everybody can follow along with. So let's start with making this work. Yes. So the basic story starts with the deformation of associative algebras. I will tell it in very elementary terms quite quickly, so we are up to speed. It consists of a three-step process, the deformation of associative algebras. Well, we start with an associative algebra itself, which is our algebraic structure, to which Hochschild in 1945 associated his Hochschild co-complex, which computes a certain cohomology, the Hochschild cohomology, not to be mistaken with the Hochschild homology, which I will not talk about in this talk. But we had this co-complex with a nice cohomology to our algebraic object, and then Gerstenhaber noticed in the 60s that this had an operatic structure from which he defined the Gerstenhaber brace. This is a higher structure on the complex, which induces a bracket, a Lie bracket. And this Lie bracket is the minimal information that we need to parameterize all deformations of our original associative algebra, and it does this through the Motherf-Cartan equation. So the process of deformation is a way of parameterizing in a nice way a whole continuous family of algebras that we consider as being very nearby or very related. So the idea is to start from an algebraic structure, find a complex with a nice higher structure, such that we have a parameterization through an equation of all these deformations. So I will go through this in steps, but first we generalize slightly from associative algebras to linear categories. They didn't do this back then, but this works completely the same, as I will show in this presentation. So maybe let's start with the basic idea. What is a non-unital category? Well, the units they will be present, but we will kind of sweep them under the carpet the whole talk, so we won't get into them. But it consists of data. The data underlying it is a linear graph. For those of you who do not necessarily like enriched category theory or category theory at all, you can just consider this as a vector space, the underlying data of an algebra. But we draw this as a point, so we already start with the drawings. And to make it concrete, a linear graph is simply a set of objects with, instead of having a set of morphisms between two objects, we have a linear vector space of morphisms. So if the set of objects only contains a single point, you have the linear graph is simply a vector space. So it's a slight generalization. And secondly, in a category or an associative algebra, we have this multiplication map that we want to be linear. We can write this simply as a map from the tensor product of the graph with itself to itself. So this is we can see this as a map of two vectors, of vector spaces, or if we want to do this with a linear graph, we want to tensor over the set of objects, which concretely means that we take a direct product, a direct sum, over all these morphism spaces for which the domain and the domain and the codomain match up. So for those of you this is perhaps confusing, just think of this as a vector space and its tensor product, and then leave out the objects. Nevertheless, we can actually draw this quite simple in the form of trees, where we say, okay, the operation of the multiplication is simply taking two inputs in our graph and then making a new input, which we call its composition. What we also know from a category is that it will be associative, which means that this graph, this diagram will commute. What does it do? It multiplies the first two components and then the results, or it multiplies the last two components and then the results. Well, using this setup of trees, we can write this also relatively simple in the following way, saying that we can plug or graft one tree on top of the other, and associativity says it doesn't matter if you plug it in the first input or in the second input, this will be the same. But we, of course, made this in an algebraic version, so we wrote this as something that we can turn into 0. Okay, so that's the algebraic object we started from. The next thing Hochschild did was associate a complex to it. So we start with what is the underlying graded object. Well, he was inspired by this idea of looking at operations of certain arities. So let's say the end component of our Hotshot complex contains those maps which take the end tensor product of A with itself to A, which means it's sort of taking n inputs of A and creates a composition of these n inputs. So in the setup of linear graphs, we simply have to take into account all these objects, take an n+1 tuple of objects, and see that the domains and codomains nicely match up. It's quite simple. You can even keep this, this writing. One way to interpret these elements, which is very useful in what we will do the whole time, is interpret them as in the form of a drawing. In this sense, we again obtain trees because we just take n inputs of A and create a single output. So this easily shows that the multiplication itself is an element of the complex of degree 2. Why? It takes two inputs and creates a single output. Now the question is, we have a graded object. How do we make it into a complex? We need a differential. So the differential would take an element of degree n, so it means an operation with n inputs, and make it into an operation with n+1 inputs. Well, we have this multiplication. So one of what we could propose is the following: just simply find all compositions you could make with our starting operation and this multiplication. So you can put it on top of it, or you can put a multiplication on top of the starting morphism here. And this creates 1 plus n, n+1 inputs. Of course, what we do for differentials, you take a sum over it, and you have to find the correct summations. So I have a question from Karim.
Sorry,
No.
What you're adding and subtracting and where and what all these are. So can you illustrate this a little bit in the case where your A is not a category but an associative algebra?
Then it would look exactly like this. It means that you, that's the nice thing about these drawings. They are quite universal, supposedly. But the idea is that if you would put here an A and put all these inputs to A, then you have to just tensor these vector spaces. So you have a map from A to the tensored with itself n times. And then you take another tensor with the first one here. So you have a tensor product of A n+1 times, and to the last n times you apply this function theta, which is simply a function. So you create out of an A to the n, you create a single A element in the algebra A, and then you multiply it with the first element that we didn't use.
On a previous level, so what are these A, x0, x1, and so on? So in the case of where A is an algebra, what should I think of that?
You could see this as a consecutive tuple of n composable morphisms. So maybe let's write it down. I hope I don't know if people in the crowd will see. You could see this as having this simplex of n morphisms that compose. So the only demand we ask is that we have the x0, but that this one has to be the same for the x1 and the 1 and the a2. And those are elements in the set of objects of my linear graph. So a linear graph can, for example, be I have 3 objects. And then instead of looking at all the arrows between them, we say, OK, there's a vector space of arrows between them. And the linear graph is all these objects together with a vector spaces of objects between them. So in a
associative algebra,
yes.
And then it generalizes. And I would like to know what, in the case of an associative algebra, any of these things would look like. I don't see any algebra coming in.
Well, in the set of algebras, I don't think I fully understand your question. The thing is, what we here say is we take a tensor product of all these ones, and in the case of algebras, you just simply take a vector space tensor product of your vector space that underlies your algebra. And then what the first tree says is we start out from this. We start out from this as an input. And first we go to A, but apply here the theta to this part, which results in a single element here. And then we apply the multiplication of the algebra that we started from. And the only thing that we do with linear graphs is we make this a bit more graded, where we bring in these sets of objects, but eventually we still work simply with tensor products of vector spaces on which we compose them, which we apply functions to. So that's the reasoning behind. So you could write this out. Normally, the Hochschild differential is written out element-wise, where we start out with n elements or a tensor product of this, and then we write out what happens that every tree spells out. But the nice thing in here is that we do not need to work with this element-wise idea anymore, but we simply could use this graphic representation. I hope it clears up a bit of what's happening. But I will continue. So this is the graphical tree representation, and what Hochschild showed is that this indeed finds a differential on this complex. And what is essential in the proof is if you do this using the trees and you plug one tree into other and you compose this twice on the same element, well, at some point you will have to use that we can switch these trees from inputs. And that's the only thing that's necessary to obtain that this is equalized to 0. OK, so we have a complex, and we call this complex Hochschild complex because it computes the Hochschild cohomology. And this has almost become a field on its own. I think I even saw online that there was at some point even a full conference here at the University of Antwerp on the use of Hochschild cohomology in, for example, non-commutative algebraic geometry. And it's really become widely used. And I'm sure people in the online audience there are quite some experts perhaps on the topic. But I will just refresh a couple of things that that I think is useful. Well, first of all, Gerstenhaber already showed that this complex computes the X modules of the algebra or the category as a bimodule over itself. So it means that we can have this very concrete complex, and it computes this derived functor of the Hom. Secondly, it's, for example, used to characterize smoothness of affine spaces. So there is the Hochschild cohomology plays a role in the classical case of commutative algebras, where it characterizes smoothness. And then you could argue that in the non-commutative case, this is also a good way to characterize smoothness in non-commutative algebraic geometry. So it forms a bridge. And then thirdly, it's a lot used to parameterize algebraic deformations. So that's exactly what we're at this point doing in this talk. So I will say some more about this last part. So we have this complex, we have this cohomology that connects also to the derived functor interpretation. But Gerstenhaber defined something extra, an extra structure on this complex, which he called the Gerstenhaber brace. So far as I know, the brace name just comes from the fact that he uses this notation in their braces. So there's not necessarily a deeper meaning. And what is it? It takes, instead of being an operation itself, it's an operation on the complex, meaning it takes two elements of the complex and creates a new element. So it takes two operations, for example, with n inputs and m inputs, and it makes a new operation. So one of the easiest way to do this is to simply plug one operation on the other one and take a sum over it with relative signs. So that's exactly what the Gerstenhaber brace does. It simply puts one on top of the other in all possible ways and takes a sum over it. As you can see, it's not at all symmetric, and it's also not meant to be symmetric. Because what he showed is that, well, okay, that's first maybe if we take something with n inputs and with m inputs, well, that's a degree n element with a degree m elements, and we make it into an operation which has n plus m inputs, but you lose one by plugging in. So it means you have n plus m minus 1 inputs. So we have an operation of degree minus 1, which will play a subtle role. But what he showed, first of all, is that if you take the symmetrization of this Gerstenhaber brace, which we call the Gerstenhaber bracket, this will be a Lie bracket of degree minus 1 on the complex itself. And interestingly enough, he showed that, well, m is an element of our complex. If we apply the multiplication with the brace to itself, we get 0. And we showed that the differential, you can actually obtain it directly using the Gerstenhaber bracket and the multiplication. Yes.
What's the exponent in the...
This thing here?
Yeah.
It's a permutation. So
Okay.
the reason why I put it here as a permutation is if you take an element of degree n and m and you permute it, you also have to do a causal sign,
Okay.
which you cannot put if you don't exactly name the. So it's a sign issue, but you just say put the first one here and the second one there, and then minus the second one here and the first one there.
Okay.
So it's just popping everything around that you can have. And thirdly, which is most important, is that if we take a desuspension of this complex, which we have to do because we want to mitigate that degree minus 1 thing, then we obtain a fully fledged dgLie algebra, meaning we got a differential, a Lie bracket, and this will be, and the differential will be derivation with respect to our brackets. Okay, this is all quite nice. We have a higher structure, but how do we find deformations now? Well, and that's where the Maurer-Cartan equation comes in. This is an equation that sort of pops up in a lot of fields of geometry, and it was generalized for the dgLie setup, which seemed like the correct place to do this. And I will just define what it is. Well, it's an element in our complex of degree 1 that satisfies the following equation. So you take the differential, and then you take the Lie bracket, but because the Lie bracket is anti-symmetric, you have to take 1 over 2. That's the amount of permutations you can do with the inputs. This is good, but let's rewrite this for our case. For the Hochschild complex, we can take out the desuspension, meaning Maurer-Cartan element is of degree 2 in the original complex. And we can desymmetrize our brackets because we've already defined it as a symmetrization. So this is a nicer equation. Why? If we work over fields of characteristic non-zero, then this does not create a problem. And there we have a problem in characteristic 2, for example. So that's one of the ways to do it. And then you can actually already see that we already know a Maurer-Cartan element, namely the multiplication itself. It is in degree 2. We know that with the brace of the m with itself is 0, and it's quite easy to see that the differential will also be 0 on the multiplication element. So this is what we call the trivial deformation, because it won't change anything to our algebra. So we could see that as the sort of zero of the Maurer-Cartan elements. Let's write this out more concretely. It means that our Maurer-Cartan element is an operation with two inputs, one output, and we wrote explicitly using trees how the elements, how this equation is written explicitly. And okay, you can look at this. It's always to compose M and M prime, but we could rewrite this in something that's quite a familiar sight. If you de-distributize this whole thing above, you get a nice thing which shows that actually M plus M prime will be an associative composition on our category. So this simply means that if we have a Maurer-Cartan element, it corresponds to a new algebra structure on our category, on our linear graph, which is very similar to the one we started from. And this is what we exactly call a deformation of our original structure. We find an extra component such that we obtain together, because the component itself alone won't be associative, but it will only be associative in the addition. Okay, so that's sort of how the classic story goes for deformation theory. We have an algebraic structure, we have a complex, which has a higher structure, which parameterizes through an equation all the deformations. Well, as I said, we don't want to stop there, and Gerstenhaber-Schack wanted to go from a small, they started with an algebra, of course, from a single small linear category, and we want to go to a presheaf of categories over some small category U to the category of linear categories and linear functors. So for example, let's make it very concrete. This is a small category that I call iso. It has 2 points and two non-trivial morphisms in them, and they are each other's inverse. So this actually computes two objects that are isomorphic to one another in a non-trivial way. So if we take a presheaf over it, it consists of 2 linear categories and 2 functors between them, which are each other's inverses. So the presheaf or representation of this category is an isomorphic pair of functors. So the question is, how does the deformation of an isomorphic pair of functors work? So that's what we do with the presheaf of categories. So the question is, what is the complex associated to it? Does it have higher structure? And how do we control all of its, how do we parameterize all of its deformations in a sort of moduli space? Okay, so this is something that Gerstenhaber-Schack set to do. And let's first maybe look at what is the data that underlies the presheaf that we have. Well, in the first place, we have 2 linear categories, which means 2 linear graphs with 2 multiplications and units, which we sort of ignore. And then we could say, okay, we could put these in sort of local Hochschild cohomology complexes for every category AU. It looks like a lot of data, but if you ignore the objects, you just get the tensor product for AU with itself to AU, which is simply the Hochschild complex for AU itself, the small local category. And the same you have for the multiplication of V. So you have local Hochschild complexes, but we also have these functors. And a functor, what does it do? It takes a morphism from x to y, and it transports it to a morphism from fx to fy. So we also change the objects. So we could write this simply in the following way. It's from the tensor products, the vector space of morphism from xy to the vector space of morphism where we change the objects. This is sort of it makes it more refined, I guess, because you could change some set of objects here and there. And the same thing here for FV. And this was, we want to write everything in this Hom way, but take into account also these objects. So that's what serves as a motivation for the Gerstenhaber-Schack complex, which is defined as a bi-complex. So you have you have in both directions complexes, and then we will take the totalization by taking the diagonals. So how is this defined? Well, the Hotshot complex takes a p simplex in our category, and then turns it into a single output. Sorry, a Q simplex, or in this case, it will Q simplex. But what we now also can do is we can take a P simplex in the small category that we started from, and then apply the presheaf to it. So you have almost two directions to go in. And that's exactly how this complex is defined. We have these Hom spaces where we take the Q tensor product of A with AUP locally with itself, and we go to a new local category by applying the presheaf to a P simplex in our small category U. So it's a sort of, it looks like a lot of data, but I will try to give you a way to look at this more clearly, which is why we love drawings. But let's, well, of course, we take a product over all these things just because it's very graded, But the next thing is, well, let's draw this again. We could draw this in the form of trees. Okay, so we go from Q simplex and we turn it into one new simplex. And I've also written, I've written all the objects. But it feels a bit awkward because, well, the P is nowhere mentioned. And in the presheaf case, these are not that interesting. So somehow there's information missing in this drawing, because you have a P and a Q. So one of our key insights that sort of gained us a lot of intuition to how to solve this is to simply write this in as a rectangle instead of writing this as a tree. Because we have a one direction up top, but we also have a direction perpendicular to it. So we take a Q simplex above with the correct objects. And then we apply on the one side, I have a P simplex, and I can either first apply the presheaf and then compose these functors, or I can first compose inside the small category and then apply the presheaf. And that's this side. So we go from something with P inputs to something with one output. So it's a bit two things at the same time. You compose vertically and you compose horizontally. And this will make the whole all the things that we came up with a lot clearer. So we go from a calculus of trees to a calculus of rectangles, which is essentially really what I will do in the next slides. But maybe some facts and observations. We have a bicomplex. We've not yet defined the differential. We could write these multiplications. It will be in the 0,2 components. And it will have two inputs above, but it will be flat on the sides. It won't change the objects at all. So it will be, I call them equalities, so you can just interpret them as a flat rectangle. And then the functors we interpret as having one input and one side input. So we can say this as these rectangles, these squares. Okay, and secondly, we also have that the Gerstenhaber-Schack complex generalizes the Hochschild complex, because if we look at the component 0n, we end up with a sort of product of all the Hochschild complexes of the local categories. So you see, we want to really make from a small thing a single category. We want to go to a whole system of categories and take everything into account at the same time, because we would like to deform everything at the same time. Okay, and then what's nice is we can use this calculus of rectangle to define, to draw the presheaf relations. On the one hand, you have this associativity, which we could have done with trees because they're flat anyway. So the side conditions we don't care about. But we also have that the functors will have to commute with the multiplication, because a functor by definition says either I do apply the functor and then do multiplication, or I first multiply and then apply the functor. So this is a nice way of writing this. And then a third thing is a bit of an awkward property, where if we apply two functors, well, we could you could also have first composed inside the small category U and then apply the functor. So it's sort of creating two f's into a one, which is sort of you start from a composable arrow u v here, and we apply the functor fu fv, or we could have composed them immediately u v here and then apply the presheaf. So this is a rather awkward situation, which we will resolve later on. But the Gerstenhaber-Schack differential that Gerstenhaber-Schack defined in the 80s consists of two components. We have a vertical Hochschild differential, which will add 1 to the vertical inputs, and we have one that will add 1 to the simplicial one will add 1 to the horizontal inputs. And these together, they showed to make a differential, so they square to 0. Well, we can draw these differentials quite simple. So we start out with an element of the complex in PQ, and we want to make Q plus 1. What we did with the trees was we plug the M underneath it or on top, which we do as well. But as you can see, there would be some open spaces, and we fill them up with Fs. So to mitigate this, on top, it doesn't really matter because the sides are flat. So next to it, you just place units. But these, the first and the second one, they need these functors to make them into a full rectangle. Otherwise, there would be holes in them. Then the simplicial one, okay, we want to add 1 to the vertical input. One way to do it is add a functor at the bottom or a functor on top, which is fine because now we have 2 inputs here, but in the presheaf case, 2 inputs can be turned into 1 as we saw before. And then here you've also, in the middle one, you've also an awkwardness where you first compose inside a small category and then apply the presheaf. And then you actually want to do exactly what we did here, but then turn on its side. We first would take one at the, from the sides. So if you turn this, for example, on its side, you get this one, but then without the multiplication. If you turn this one on its side, you get this one, but then without the multiplication. And then these ones are also sort of similar. Okay, so that's great. We got presheaves, then we make into a complex. We have its cohomology. The issue will be that if you compute its cohomology, you expect it to control the first order deformations of A as a presheaf. Of course, I've not really defined what first order deformations are. Nonetheless, this gives us the idea that the Gerstenhaber-Schack complex is not the right complex to look at because it's too big maybe. But on the other hand, they showed that it does compute the X modules of A as a bimodule over itself. And that gives us the idea that it is the right complex to look at. So let's look at what goes wrong. It goes wrong, well, if you look at the second component of the Gerstenhaber-Schack complex, which is a bicomplex, we have 3 components. And well, the multiplication is in the first one. The functors are in the second one, but we sort of have an unknown in the third one, which is lacking, but which shows up in the homology. So the question is, the plot twist is, what is this? And we call them twists. So these twists will make us look at the presheaf as a more generalized version of the presheaf. And we actually know this one. And that's why we say deformation theory and the Gerstenhaber-Schack complex motivate us to go from presheafs of categories to linear prestacks, which are functors which do not satisfy the same relations exactly, but up to isomorphism. In the sense of category theory, we go from 1 categories to 2 categories, where we look at, instead of strict functors, we go to pseudofunctors, or weak functors, they're also called. So we have a small category, and then we have the 2 category of linear categories, linear functors, and then linear natural transformations. Okay, I'm quite sure not everybody is very aware of what a pseudofunctor is or what this means in this context, so I will write it out very explicitly. A pseudofunctor over a small category U consists of linear categories for every object in U. So we have a linear graph with a multiplication, a unit that we sort of ignore. And then we have for every morphism a linear functor going between these categories. I forgot to write the up top here. So what we always do in the presheaf, I don't necessarily know exactly why, but you turn it around. It's sort of maybe something everybody does. And then this is what a presheaf would be. But instead of having the relation that the functor commutes with the composition in the small category U, we wanted to commute up to a natural isomorphism. So it sort of letting there be automorphisms between this equality instead of being the identity. So we loosen this a bit up. And this is what we call twists. So for every two composable morphisms in U, we apply the presheaf and compose these functors. Well, this is naturally isomorphic to the one if we first composed in the category U. Now, this creates an ambiguous situation in the same way that the multiplication has an ambiguous situation, and we call this a co-cycle condition. It's sort of an associativity condition for these twists. Either I can twist, if I take three composable arrows, either I can twist the first two and then the result, or I can twist the last two and then the result. And we want this to be associative, so we ask this to commute. And that's how we would write it in diagrams, but I want to write it using rectangles to promote my work. So one way is to rewrite it as follows. Well, the multiplication will be an element of the Gerstenhaber-Schack complex, a 0, 2. And the other one, the functor, will be in 1, 1. And then the natural transformation will correspond to this shape. It takes two morphisms UV, composes this into a single morphism. And it consists of a collection of elements taken in the algebras. I know this is rather vague at the moment, but if you would write it out concretely, you would see that this is the underlying structure of a natural transformation in the linear case. But what is nice, we can rewrite all these relations. We have the associativity relation, which still holds. We have this functorial relation that we still want. But then the question is, when will this be a natural transformation? Well, that condition we could write as follows. It will have to commute horizontally with the functors. But because we then have two outputs at the bottom, we have to place a multiplication underneath to make it of the right shape. So what this does is simply say, if you have a multiplication, you can just just commute the twists with the functors. And then the associativity or the co-cycle condition for twists, you see here, this is simply the associativity turned on its side. But we have to again put a multiplication underneath it and add a functor in to fill the holes up. So in this sense, this is also the definition of, well, not exactly a pseudofunctor. This is going to be of a lax functor. And a pseudofunctor says that TCs also need to be isomorphisms. So that's rather difficult to explain in the rectangles case. You can, but it takes us to a whole different world, which we will stay out at the moment. So in fact, I could have done this whole thing for lax functors instead of pseudofunctors. And if we look at the category iso, a lax functor over iso is a adjunction of two categories. So we're actually now looking at how does the deformation theory of adjunctions look like. That's sort of the core of what we're doing. So the linear prestack we can still define the Gerstenhaber-Schack complex, but what will the differential be? And that's a paper by Dinh and Wendy Lowen that they did in 2018, where they redefined this differential, but a lot more complex. Why? We still have a first component of the Hochschild. We still have the simplicial component, but they won't square to 0. So they remedied this with higher components that make an infinite sequence, but it will, because of the bi-grading, it will be convergent everywhere. So although this generally will be a power series, if you look at it per element, it will be definitely convergent. Or you could define a filtration on it for which it is convergent. Okay, so these differentials, how can we draw them? Because I won't write them out explicitly, but we could draw them simply the same as we did before. The Hochschild component stays the same, but then the simplicial component will be different. Well, we remember these ones down below, but now we have to sort of remedy these two outputs by sticking a twist to the side, and then we have two outputs at the bottom, so we have to stick a multiplication underneath. Yeah.
Why do you always have to have this one thing at the bottom?
Because that's how the complex is defined. For example, you could
It's on to A. Okay,
yeah,
right, yeah.
it's to A, because it could have, of course, you could define it to multiple outputs, but then it won't control this deformation theory anymore. Because then you would go into, for example, co-algebraic things would come up. It will be more properatic instead of operatic. Whole theory is a lot more Frobenius type stuff, and this will stay in the algebra case. But so you see, we have implemented here a C, and we needed a multiplication also on the other side. And here, what we have this awkward situation, we can now write out explicitly. We can put on every height a twist and take the sum over all these options and fill them up with functors. But then, of course, we also have to put a multiplication at the bottom. And this is nice, but this does not square to 0, which is why these remedying terms had to be implemented. I'm going to look at the clock for a second. Oh, I will have to go a bit fast, I think. OK, so one way to do what we did was we defined this thing by saying, let's try to make fill a rectangle with our input rectangle together with all any combinations of functors and twists and a multiplication at the bottom. Well, in their paper, they showed that this does define a differential, and moreover, that it does compute the X modules. And what is mostly important is they showed that it does control first-order deformations of A as a linear prestack. So it actually shows that instead of looking at linear presheaves, we have to start with these linear prestacks, and the Gerstenhaber-Schack complex is the right complex to do this. Now the question is, well, first-order deformations, that's nice. We want to have all deformations. So that's why we look for this higher structure. What is the Gerstenhaber-Brace analog? Well, instead of going from calculus of rectangles, it won't be the same as the calculus of trees because we lose some operatic things. And the reason for this is, for example, if I would simply do an analog of the Gerstenhaber-Brace, we have the problem of empty spaces, and we have these side components that are not correct. So what do we do? Exactly what we did with the differential. We use our multiplication, functors, and twists to complete this in a very natural and nice way. We just fill it up as you would try to. Of course, you have to take a summation over all possibilities, find the appropriate sign, and then show that it does do what we want it to do. Well, here's, for example, one of the terms that would be implemented. You have a twist here, you have a twist here, you have a twist here, some functors in between, and you have those two morphisms here. But this won't be the final result. What we came up with is, well, the brace for the Gerstenhaber-Schack thing, the Gerstenhaber-Schack complex will look as follows. So it's sort of any way we can compose one multiplication at the bottom and two of our inputs together with all f's and c's that we can imagine. Why do we use the c's and only the m1s? Well, the c can turn an input from above, takes one away because it has 0 inputs on top, but it creates an extra input on the vertical side. So we use the c's to close down all the horizontal, the vertical inputs and create horizontal ones. So that's one thing that we did, and then we look, for example, at the symmetrization in a very direct way. Now the question is this a Lie structure? And unfortunately, this does not define a Lie structure. Why? Well, if you take the Lie relation, it won't be equal to 0, but we will be able to extend this to a fully fledged L-infinity structure, which means that we have homotopes for all levels, which means if we, for example, have the Lie relation, it won't be 0, but it will be the boundary of a higher homotopy. And those will be in a relation with the other ones up to the boundary of a higher homotopy, and so on, and so on, and so on, and so on. So we have that every component, every homotopy is a power series of an infinite amount of components, and we have an infinite amount of homotopies. And that's the full L-infinity structure. Let us look a bit how we came about. Well, this is what we proposed in the case of the higher homotopy, the P3. It will not be, we will symmetrize it later. So what we again do is we do a multiplication. We place them in the square, in the plane, so as to form a nice rectangle. And then we fill them up with f's and c's as much as we can. And then we sum over it with appropriate signs. Well, you see here, for example, one thing, and that is that you cannot simply put any way you like there, because if this one comes up top of here, well, if I would then permute these two, you would have terms coming, that are you have terms that will cancel each other out if you take the symmetrization. So you sort of still want to place them in a fixed order, such that afterwards we can symmetrize them for the higher homotopes. So the idea behind this is a bit very simple. You see the Lie bracket will be all possible tilings of a rectangle using one multiplication, or input rectangles, and any amount of functors and twists. And the same is for L3. And then, of course, our proposition for Ln, the nth homotopy will be exactly this. The tilings in the plane of all, such that there's exactly one multiplication, the right inputs, and any functors and twists. And we showed in a recent paper that the desuspension, of course, we get from the Hotshot complex, the same idea. Well, this, of course, this we defined to show to be an L-infinity algebra. And that's nice. Why? Because even the L-infinity algebra or also called a strongly homotopy Lie algebra, also parameterizes algebraic structures through a generalized Maurer-Cartan equation. Instead of using one bracket, we have now an infinity amount of operations, and we call a Maurer-Cartan element an element of degree 1 fulfilling this equation. And again, you see this factorial coming up, and that's because these are anti-symmetric, these braces. You have the same inputs everywhere, and the factorial is the number of permutations you have on a set of n elements. We rewrite this in our case, and you see that, for example, that the Maurer-Cartan element corresponds to an element of the second degree, so it contains a multiplication, a functor, and a twist. Well, I would write them prime everywhere here. I think I forgot. And then we can desymmetrize our ln's into these pn's, which is again nice because now we don't have issues with characteristics and dividing by n factorial. Okay, and what did we show at the end of our paper? We showed that this indeed controls deformations of A as a linear prestack through the Maurer-Cartan equation, in the sense that if we take an element of degree 2 in the complex, well, this will be in a desuspension an element, a Maurer-Cartan element, if and only if we add them component-wise, we again obtain a linear prestack. So this is to some extent deforming the categories locally and the functors and the twists all at the same time in a single complex, which is exactly what we were looking for. So this sort of completes our story full of twists. We go from a linear prestack instead of a linear presheaf to the Gerstenhaber-Schack complex, which computes its x bimodules, which has a higher structure of an L-infinity algebra, which governs the deformations through the Maurer-Cartan equation. And that is the story that I will present here today.